Hello, and welcome to the Sleepy God, and thank you for joining me on this quiet journey into the heart of emptiness. Take a deep breath and settle in. Let the day slowly fade into the background, leaving behind a moment of stillness. Tonight, we explore an idea that may seem paradoxical at first. Can nothingness have a shape at all? The very word nothing often feels like a void in itself, a concept so empty that it resists comprehension. Yet, when we look closely, nothingness reveals many faces, and it turns out that in some senses, it can indeed have a form. Now, picture this. You're holding a smooth stone in the palm of your hand. Its surface is cool, solid, defined by edges and angles. But think of the space around the stone, the air that fills the gaps between your fingers, the emptiness that exists between its surface and your skin. Is that emptiness something? Or is it truly nothing? If it's something, can it be described? Can it have a shape? This question is not only philosophical, it reaches deep into science and mathematics, where nothingness is given structure, form, and even function. Before we embark on this journey, let's first consider what we're asking when we ponder nothingness. Is it simply the absence of something, a void with no definition, or could it be something more subtle, more intricate? The ancient Greeks argued over this very question, and in their debate, we find the roots of our modern understanding of the empty spaces that surround us. At the heart of ancient philosophy, one name stands out: Parmenides. Parmenides didn't trust nothingness. He argued that what truly exists must be full, unchanging, indivisible. For him, none being nothing could not even be thought of, let alone spoken of. If something were to vanish into nothingness, then, by his logic, it would be impossible for it to reappear. Change, in Parmenides' world, was an illusion and the very idea of a void. A space where nothing exists was anathema to reason. To him, the cosmos could only be complete, unbroken, a sphere with no gaps or empty spaces, in stark contrast. Another current of thought was brewing, the ideas of the atomists, led by Leucippus and Democritus. They offered a radically different view of reality. According to them, the universe was made up of indivisible atoms, and these atoms moved through empty space. The void was not only real, but essential for motion. Without the void, atoms couldn't move, collide, or rearrange themselves. The absence of matter, they proposed, was not a strange, unthinkable thing, but rather a necessary condition for everything that happened in the physical world. Without the void, there could be no motion, no change, no life. These two visions, one where nothingness is forbidden, and the other where it's the very foundation of change, set the stage for centuries of philosophical and scientific inquiry. The debate about emptiness would not only shape the trajectory of thought, but also influence the very language of science. It's in this tension between full and empty, between what is and what isn't, that our story begins to take shape. The ancient Greeks weren't the only ones to grapple with the idea of nothingness. As we move into the medieval period, thinkers such as John Philoponus would challenge Aristotle's ideas about the vacuum, questioning the necessity of a medium for motion. Could motion persist without a surrounding substance? The notion of the void would continue to evolve, becoming a central focus for later scientists and mathematicians. But before we rush ahead to these later developments, let's take a moment to reflect on what nothing really is and what it might look like. Can nothingness, at its core, have any shape at all? Could it be described like the empty space around a stone, or does it remain entirely out of reach? Perhaps the answer isn't so simple, and that's part of the beauty of this mystery. As we move forward in this exploration, we'll see how the ancient debates about emptiness laid the foundation for our modern understanding of space, time, and the very fabric of reality itself. To understand the role of nothingness, we must first immerse ourselves in the paradoxical discussions of the ancient world. The Greeks, those early thinkers who laid the foundation of Western philosophy, were obsessed with the concept of being and non-being. At the core of their debate was the idea of the void, a space devoid of matter, energy, and essence. Could such a thing exist? Could there be a place where nothing happens, nothing exists? Parmenides, a philosopher from ancient Greece, did not simply question the void. He rejected its very possibility. For him, to even consider non-being was a contradiction. According to Parmenides, if you could think about nothingness, then it had to be something. He argued that reality, as we know it, must be whole, unchanging, and indivisible. Anything that could change or move, he claimed, would only do so within a complete, unalterable reality. Thus, the void, a place of change and potentiality, simply could not exist. To Parmenides, the very concept of a void implied a gap, a break, in the fabric of reality. But this gap, he believed, could not exist without contradicting the very idea of being. He saw it as an intellectual trap, a concept that, once examined closely, would dissolve into incoherence. His world was complete, self-contained, and eternal. There could be no empty space where nothing existed. Everything must be filled, whole, and infinite. Yet, even as Parmenides solidified his view, another strand of thought emerged, one that would lay the groundwork for our modern understanding of physics. This new approach was championed by Leucippus and Democritus, two Greek philosophers who dared to imagine a world made up of tiny, indivisible particles, atoms, moving through empty space. To them, the void was not a contradiction, but an essential feature of the universe. For Leucippus and Democritus, the void was the stage on which the drama of existence unfolded. Without it, atoms could not move, collide, or rearrange themselves. Motion, they argued, could not happen in a world without emptiness. The void, far from being a contradiction, was the very thing that allowed for change, for the movement of particles that make up everything in existence. This atomic view was radical for its time. In fact, it was so radical that it was largely ignored by the mainstream thinkers of the day. Aristotle, for example, would later dismiss the atomic theory as little more than a fantastical idea. But the seeds of this atomic model would eventually grow into a powerful force that reshaped our understanding of the world. In essence, the atomic theory offered a perspective where the void was not an empty, meaningless space, but an essential part of reality, a space in which the very building blocks of matter could interact and evolve. This idea would be largely forgotten for centuries, but it would be revived in later centuries, particularly during the scientific revolution, and yet, even in ancient Greece, the concept of the void was not without its challenges. Aristotle, who disagreed with the atomists, argued that motion could not exist in a true vacuum. According to Aristotle, for an object to move, it must be displaced through some medium, such as air or water. Without such a medium, there would be no resistance, and, in his view, movement would become paradoxical, even nonsensical. For Aristotle, the universe was a plenum full of matter. He believed that all space was filled with some substance, even if we couldn't see it. Empty space, he argued, was an absurdity. If you tried to create a vacuum, he believed, motion would become uncontrollable. Speed would become infinite. and logic itself would break down despite these challenges. The atomists' ideas about the void had a profound influence on the development of modern science. The debate between the idea of a plenum and a void would eventually lead to the recognition that empty space could in fact be described, measured, and understood. The struggle between these two viewpoints, Parmenides' rejection of nothingness and the atomists' embrace of it, shaped centuries of debates. It was a debate that continued into the medieval period and beyond, and it set the stage for the modern conception of the vacuum as not just empty space, but a space filled with possibilities. The intellectual battle between these ideas, which initially seemed so abstract, would eventually lead to real-world discoveries about the nature of matter, energy, and the very fabric of the cosmos. But before we move forward into the modern age, let's pause here and reflect on the incredible paradox that these ancient thinkers grappled with. They were not just debating whether nothingness could exist, they were laying the groundwork for an entirely new way of thinking about the universe. Their ideas, once so disconnected from everyday experience, would one day form the foundation of fields like quantum mechanics, relativity, and cosmology. This battle between being and non-being, between the plenum and the void, continues to shape how we think about the universe today. And in that tension, we begin to see that nothingness is not so simple. It is filled with potential, with mystery, and with the promise of discovery. As we move from the intellectual ferment of ancient Greece into the Middle Ages, the debate over nothingness and the void would continue to evolve. Though the tensions between the ancient thinkers would persist, at the heart of this evolution stood Aristotle's unyielding conviction that the universe was a plenum, filled with substance and motion. This conviction would dominate Western thought for over a millennium, and it would take both new philosophical and scientific breakthroughs to begin to break the chains of his ideas. Aristotle's theory, known as the plenum, is central to understanding how medieval scholars would frame the void. In Aristotle's view, space could never truly be empty. Every motion required a medium, a substance that filled space, allowing objects to displace it. For him, the cosmos operated as a complete, unbroken system where all motion was explained through the displacement of one substance by another. Whether it was air, water, or any other form of matter, space was always full, and there could be no vacuum, no true void. This Aristotelian view of the world was deeply entrenched in the medieval period, where it became intertwined with Christian theology. The idea that God had created a perfectly ordered, filled universe fit nicely into the medieval worldview, where nature, much like the divine order, was understood to be perfect and complete. The notion of a vacuum or empty space was seen as something unnatural, something that could not exist in a world created by a perfect God. For many thinkers of the time, the concept of the void was heretical. It undermined the very idea of a perfectly created world. However, as the centuries passed, thinkers like John Philoponus began to challenge Aristotle's notions. Philoponus, a Christian philosopher of the late antiquity, was one of the first to question the necessity of a medium for motion. He argued that motion could persist even in the absence of a surrounding substance. This idea was radical in the context of Aristotelian physics, and though it was not widely accepted at the time, it laid the groundwork for later developments. In both physics and philosophy, the rise of Islamic philosophy in the medieval period would continue to question the boundaries of Aristotelian thought. Scholars in the Islamic world were often more open to the possibility of a vacuum, and their work would eventually pave the way for the rethinking of Aristotle's model. Figures like Ibn Sina, Avicenna, and Al-Hasan ibn al-Haytham began to explore the concept of nothingness from a different angle. While they were largely influenced by Aristotle's ideas, they began to entertain the possibility of an empty space, though their approach to it was more metaphysical than empirical. At the same time, the early Islamic scholars took a more experimental approach to understanding the natural world. They built on the work of the ancient Greeks, particularly that of Euclid, Archimedes, and Ptolemy, but they also introduced new mathematical and empirical techniques. Some Islamic philosophers, like Al-Farabi, even started to consider whether a void could exist under the right conditions, even if it was an impossibility in the classical Aristotelian framework. The blend of logic, philosophy, and early scientific experimentation during this period helped expand the understanding of space and absence beyond the rigid limits set by Aristotle. This intellectual curiosity would eventually spill over into medieval Europe, where scholars such as Jean Baradin and Nicole Orazem began to probe the concepts of impetus and motion. The medieval scholars worked with Aristotle's ideas of motion, but they added new dimensions to them, suggesting that objects could have an innate tendency to continue moving in the absence of an external medium. They also raised questions about the possibility of a true vacuum, questions that would remain unresolved for centuries, but that would eventually lead to the birth of modern physics. The questions about nothingness and the void were not just abstract exercises in logic. They were tied to practical concerns. The medieval scholars were grappling with the nature of motion and the behavior of celestial bodies. The heavens, in particular, presented a unique challenge. How could celestial bodies move in a perfect, unchanging way if there was nothing to guide them through the heavens? If there was no medium to support their movement, how could their orbits be explained? This debate over the nature of space and the void took on new urgency in the early modern period, as astronomers like Copernicus, Kepler, and Galileo began to develop new models of the cosmos. Their work, which ultimately challenged the geocentric model of the universe, also began to show that the heavens were not filled with a substance, but rather they were empty space. Copernicus, in particular, proposed a heliocentric model of the universe where the Earth revolved around the Sun, and the space between the planets was empty, or nearly so. These early modern astronomers could not yet explain the exact nature of space, but they laid the groundwork for the later development of the idea of the vacuum in the 17th and 18th centuries. It would take the development of experimental science, particularly in the field of pressure and gases, to demonstrate that a true vacuum could indeed exist. And yet, even as new ideas about space and motion were taking hold, the question of the void remained. Was space a plenum, filled with an invisible substance? Or could it be empty, the canvas upon which the stars and planets moved? Could the void be a place of emptiness and potential, or was it an illusion, something that arose only from our lack of understanding? This debate would carry on through the centuries, but the work of early philosophers and scientists like Philip Ness, Alhazen, and the medieval European scholars had already begun to shift the way the world was viewed. The once rigid and complete understanding of the universe, as proposed by Aristotle, was slowly being unraveled. The quest for understanding the void, the emptiness between stars, between particles, and between ideas would continue to shape our scientific inquiries for centuries to come. The tension between these ideas, the plenum and the vacuum, was not just philosophical. It became a question of how we see the universe itself. Is the universe a perfectly ordered, full space, or is it a vast emptiness that allows for movement and change? The void was no longer just an abstract idea. It was a concept that would shape the development of modern physics, from the study of gases and pressures to the bending of spacetime itself. As the Western world continued to wrestle with the question of nothingness, other traditions were also grappling with the nature of emptiness, albeit in a very different way. While ancient Greek philosophy focused largely on the void as either an illogical contradiction or a necessary space for movement, other cultures and schools of thought took a more nuanced approach to nothingness, seeing it not as a simple absence but as an integral part of the fabric of existence. The Stoics, for instance, acknowledged the presence of the void, but not in the sense of empty space as we understand it today. Their view was deeply tied to their belief in a rational and purposeful cosmos. The Stoics conceived of a finite, coherent universe filled with a breath-like principle, often referred to as pneuma, that pervaded all things. This principle was an animating force, the essence that linked all parts of the universe in a unified and purposeful way. But what about the space outside this universe? The Stoics allowed for a vast, unbounded void beyond the universe. However, this void was not truly empty. It was a space without structure or order, but still, it served a necessary function by framing the cosmos. The cosmos, in their view, could not be understood without its boundary, the emptiness that defined its edges. In essence, the void was not something to be feared or rejected. It was simply the absence that gave the cosmos meaning. In this sense, the Stoics were some of the first to grasp that nothingness, while unfilled, could still carry significance far beyond Greece. In the traditions of Buddhism and Taoism, emptiness takes on a much deeper and more transformative meaning. In Buddhism, the concept of Nyat emptiness is one of the most fundamental ideas. But Nyat does not refer to a vacuum or a literal emptiness. Instead, it refers to the lack of inherent, independent existence in all things. Everything is interconnected, and nothing possesses a fixed, unchanging essence. In this context, emptiness is not a void that needs to be avoided. It is the ground of all possibility, the state that allows for interdependence and transformation. The famous Buddhist teaching form is emptiness, and emptiness as form highlights this idea. Things are not truly empty, but they are empty of inherent essence. Everything is constantly changing and dependent on other things for its existence. Emptiness in this sense is not bleak or negative. It is a liberating understanding that allows for the interconnectedness of all things. This view of emptiness opens the door to a dynamic universe where everything is in constant flux and transformation. Similarly, Taoist philosophy offers a beautiful and serene reflection on emptiness. The Taoist notion of wu-wei non-action emphasizes the power of emptiness and stillness. Just as the Tao, or the Way, is understood as a force that flows through all things, so too is the emptiness within objects what gives them their function and meaning. The Taoist classic Tao Te Ching suggests that the usefulness of a wheel comes not from the material of the wheel itself, but from the empty space at its center. The room is livable not because of the walls, but because of the empty space inside. In Taoist thought, emptiness is the wellspring of functionality and form. It is a reminder that absence can be just as valuable as presence. Both Taoism and Buddhism offer a radically different perspective on the void. In their teachings, emptiness is not something to be feared or erased, but something to be embraced. It is not a blank slate or a nothingness. It is the essential ground of being, a concept that allows for the full expression of existence. When we look at these different philosophical traditions, it becomes clear that nothingness is more than just a simple absence. It is a space, a condition, and a force that carries its own meaning. In the West, the void was often viewed as a problem to be solved or eliminated. But in Eastern thought, emptiness is integrated into the very fabric of life, offering a different kind of wisdom, a wisdom that sees the world not as a series of separate, static objects, but as an interconnected and dynamic whole. This approach to emptiness, where absence becomes not a flaw, but a necessary condition for existence, can be seen as a precursor to later scientific developments. For example, in quantum mechanics, the vacuum is not empty space, but a seething, dynamic field, full of potential energy and fluctuations. The quantum vacuum, much like the Buddhist or Taoist emptiness, is not truly void. It is simply a different kind of reality. These Eastern philosophies also draw attention to the fact that what is missing is often just as important as what is present. In geometry, the empty space between 2 points is not inconsequential. It's this space, or the absence, that allows for movement, change, and measurement. Just as the Taoist wheel is defined by its empty center, so too is the world we inhabit, shaped by the invisible, the unspoken, and the unmeasured. Returning to the Western tradition, we see that while early philosophers like Parmenides and Aristotle feared the void, later thinkers such as the atomists and medieval scientists began to open their minds to the possibility of a true empty space. This shift in perspective was slow but profound, and it eventually led to the acceptance of a new kind of emptiness. The vacuum. By the time of the Renaissance and the scientific revolution, the void had ceased to be an abstract philosophical problem. It had become a real, measurable entity. The vacuum became not only a scientific curiosity, but also a crucial concept in the emerging fields of physics, astronomy, and later, quantum mechanics. This shift from seeing nothingness as a philosophical puzzle to recognizing it as a fundamental part of the universe marks a key turning point in the history of human thought. As we move forward into this new understanding of emptiness, we begin to see how it is not simply the absence of things, but the ground upon which everything is built. The debates of ancient Greece, the meditations of the Stoics, the spiritual teachings of Buddhism and Taoism, and the eventual breakthroughs in physics, all converge on the same point. Nothingness, in its many forms, holds a deep, intrinsic order that guides the structure of reality itself. As we delve further into the unfolding story of nothingness, we begin to see its role not just in philosophy, but in the very structure of the universe. For centuries, thinkers debated the nature of the void, questioning whether it could be more than just an absence, a negative space defined solely by what it lacked. Yet, as they began to understand the world through mathematics and geometry, they discovered that even nothingness could have a structure, and that structure would later be instrumental in shaping the scientific revolution. It was Euclid, the ancient Greek mathematician, who first began to lay the foundation for this understanding. His work, Elements, created a framework for geometry that would last for over 2,000 years. Though his treatise focused on points, lines, and shapes, Euclid's greatest contribution was the way he framed the concept of space. For Euclid, geometry was not just about measuring distances or drawing lines. It was about understanding how space itself worked, how it could be described, and how seemingly empty spaces could be systematically understood. In Euclid's view, space was not just a passive void. It was structured. Every line, angle, and shape existed within a framework of principles that defined how they could interact. Geometry, in its purest form, required no physical substance. It was, in a sense, an abstract description of the relationships between objects and spaces. Through definitions, postulates, and axioms, Euclid showed that even the emptiness between objects had a kind of geometry, a way of organizing and understanding the distances, angles, and relationships that existed in the universe. The key to Euclid's geometry was his use of the point as the most fundamental building block of space. A point, Euclid defined, is that which has no part. From this simple idea, he constructed the entire world of geometry. But this absence of parts, this idea of a point, hinted at something profound. Space could be described without the need for physical substance. It could be organized, measured, and understood even in its emptiness. The remarkable thing about Euclid's work was that he never needed to define what space itself was. Instead, he focused on the relationships between the elements within it. A straight line, for example, was defined by the relationship between 2 points. An angle was the relationship between 2 lines. This approach allowed Euclid to create a consistent and rigorous framework for geometry, one that could describe the world even in its emptiest forms. But Euclid's geometry was not just about absence. It was about relationships. The space between 2 points might be empty, but it still had a structure defined by the straight line connecting them. Emptiness, in this case, was not simply void. It was the context in which relationships could occur, the background against which shapes and forms could be defined. And it was this structure of nothingness that allowed Euclid to make profound discoveries about the nature of space. In the centuries following Euclid, his geometry would continue to influence how thinkers approached the concept of nothingness. The idea that space could be organized without needing to be filled with physical substance became more than a theoretical curiosity. It became a cornerstone of mathematical thinking. Over time, this concept would evolve, leading to new understandings of geometry, space, and the very fabric of reality. It wasn't just philosophers and mathematicians who took note of Euclid's ideas. The implications of Euclid's work reached far beyond the walls of ancient Greek schools. In the Renaissance, as new ideas about the universe began to take root, mathematicians and scientists like Copernicus, Galileo, and Kepler would use Euclid's geometric principles to map the heavens. The idea that space could be empty, yet still have structure, would play a critical role in their understanding of the cosmos. But it was not just the intellectuals of the Renaissance who were influenced by Euclid. His ideas would eventually inspire the scientific revolution, where the principles of geometry would be applied to describe not only the empty space between the stars, but also the laws of motion that govern the universe. The empty space between celestial bodies, once thought to be a void, became a place of interaction, guided by the invisible forces of gravity and the geometry of space itself. As we continue to trace the evolution of thought about the void, we move from the abstraction of Euclidean geometry to the more tangible, experimental world of modern science. It would take the work of astronomers like Kepler and Newton to further expand the notion of space as not just empty, but full of potential forces and interactions. Newton's laws of motion and gravity, built upon geometric principles, showed that empty space was not devoid of influence. Instead, it was shaped by the gravitational pull of massive bodies. And that pull could be measured, calculated, and understood. But before Newton, there were other thinkers who, inspired by Euclid's work, began to see the relationship between nothingness and the universe differently. These early pioneers, like John Philoponus and Jean Baradin, started to explore the implications of motion without a medium and the possibility of a true vacuum. Their ideas, though not widely accepted at the time, foreshadowed the eventual breakthroughs of later scientists who would come to see the void, not as a simple absence, but as a field of possibility. In the end, it was Euclid's methodical approach to space that provided the foundation for these later developments. By framing emptiness in terms of relationships rather than substance, Euclid opened up a new way of thinking about the world, a way that would later influence everything from the laws of planetary motion to the development of quantum mechanics. His work proved that nothingness, far from being an unknowable mystery, could be structured and understood. Thus, Euclid's geometry becomes more than just an abstract theory. It is the key that unlocks the door to a deeper understanding of the universe. Even in the absence of matter, geometry finds its place. And as we explore further into the realms of physics, we will see how this structured nothingness continues to shape our view of reality. The story of nothingness takes another profound turn when we arrive at the concept of zero. What was once considered a simple placeholder in ancient number systems would, over time, evolve into one of the most powerful and transformative ideas. In human history, zero is not just the absence of a quantity, it is a profound mathematical tool that anchors entire systems of calculation, measurement, and understanding. In ancient Mesopotamia, around 3000 BCE, early scribes, using the Babylonian number system, encountered a challenge. Their system, based on the number 60, was highly effective for astronomical calculations and trade, but it lacked a clear way to distinguish between a number like 1003 and the same number with a different positional value, such as 1003. The solution was simple but revolutionary. They used a space or a symbol to mark the absence of a value in a given place. This early placeholder symbol, often represented by a pair of small wedges, allowed the Babylonians to write large numbers with clarity and precision. However, this was not yet zero as we know it. It was merely a placeholder to keep the rhythm of the number line intact. It allowed them to distinguish between different quantities, but it did not yet have the power to function as a number in its own right. For centuries, this symbol would remain a convenient notation rather than a concept with its own set of rules and operations. The true leap forward came in India, where mathematicians took a crucial step by treating zero not just as a placeholder, but as a number in its own right. Around the 5th century CE, the Indian mathematician Brahmagupta wrote about zero as a fully functioning number. He described how adding zero to a number left it unchanged, how subtracting zero left the quantity as it was, and how multiplying by zero resulted in zero. These were foundational rules in arithmetic that would allow numbers to become much more than just counting tools. They would become a language capable of describing the universe itself. Brahmagupta's work marked a paradigm shift. Zero was no longer just a space to indicate an absence. It was a number that could participate in arithmetic in the same way as any other. His rules were not entirely aligned with modern arithmetic. He, for instance, did not yet fully grasp the concept of dividing by zero, but his recognition of zero as a number with its own behavior set the stage for the mathematical developments that would follow. As zero spread through the Islamic world, it took on new life. Scholars like Al-Khwarizmi and Al-Farabi, building on Brahmagupta's ideas, further developed the concept of zero within the broader system of Arabic numerals. The word sifr, which meant empty or nothing, became associated with the concept of zero. This term would eventually make its way into Latin as zephyrim, and then into European languages as zero. The power of zero began to radiate outward from the Islamic world, eventually reaching medieval Europe, where it would reshape the way people understood numbers and, indeed, the world. But despite its transformative potential, zero was initially met with resistance in Europe. For centuries, many in Europe stuck to the old Roman numeral system, which lacked a symbol for zero and used letters to represent numbers. The new Arabic numerals, which included zero, were viewed with suspicion. Authorities in some cities even banned them, fearing that they might encourage fraud after all. The smooth curves of Arabic numerals were easier to alter than the rigid strokes of Roman numerals. However, as with many innovations, convenience eventually won out. By the 12th century, the use of Arabic numerals began to spread across Europe, largely due to the efforts of scholars and mathematicians like Fibonacci, who championed their use in his book Liber Abaci, 1202. Fibonacci recognized the practical advantages of the new system, particularly the ability to perform multiplication and division with greater ease, and he encouraged merchants and accountants to adopt it. As zero became integrated into the number system, it slowly but surely transformed mathematics. Zero's true power emerged with the advent of algebra. In algebra, zero becomes more than just an empty placeholder or an absence. It is the fundamental, the building block of equations. The ability to use zero to represent an unknown quantity allows for the development of equations that describe everything from the motion of planets to the flow of electricity. Zero becomes a marker of balance, of equilibrium, and of limits. Yet zero's influence would only grow more profound with the work of calculus. In the 17th century, Isaac Newton and Gottfried Wilhelm Leibniz, building on the work of earlier mathematicians, developed calculus by treating quantities as approaching zero. This concept of limits, the idea that a function can approach a value as closely as desired but never actually reach it, allowed for a more refined understanding of motion, change, and growth. Zero, in this sense, was not just a number. It was the threshold at which the language of calculus could speak meaningfully about the infinitely small and the infinitely large. The development of zero as a number and its integration into the world of mathematics would have far-reaching consequences. It would allow for the precise measurement of time and space, the development of complex algorithms, and the modern understanding of physics. Zero would become the very foundation of our ability to navigate the universe. Without zero, there would be no way to measure the vast emptiness of space or the infinitesimal particles that make up the matter we see. It is zero, more than any other number, that allows us to describe the very fabric of reality. Zero's journey from a placeholder in Babylon to a fundamental concept in modern science is a testament to the power of ideas. It is a reminder that even the simplest of concepts, what we once thought of as an absence, can carry immense significance. Zero anchors our understanding of the universe, holding together the fabric of space, time, and numbers. In its emptiness, zero provides the structure that holds everything in place. In the next chapters of this exploration, we'll see how zero's quiet power continues to shape the world, not just in mathematics, but in physics, where the very concept of a vacuum is redefined by the quantum world. But before we leave zero behind, it's important to recognize that this little number, which once seemed so insignificant, is anything but empty. It is, in fact, the calm center around which the whole of mathematics and science turns. As zero transforms from a mere placeholder into a number with profound implications, we move toward a powerful conceptual leap that would shape both mathematics and our understanding of the world itself. The creation of the number line. This seemingly simple concept would revolutionize the way we think about space, movement, and measurement. The number line begins with a single, unassuming point, 0. From this point, we stretch out in both directions, marking numbers in discrete steps. The result is a continuous, ordered space in which each number has a distinct position relative to every other number. The simplicity of this idea belies its incredible power. By assigning a location to each number, the number line allows us to visualize and understand not just the relationship between numbers, but the structure of space itself. The number line is more than just a tool for representing numbers. It is a bridge between the abstract world of mathematics and the tangible world we experience. Every measurement, every quantity, every dimension can be thought of as a position along the number line. From this simple structure, we can describe not just numbers, but the positions of objects in space, the passage of time, and even the motion of the stars themselves. But the true genius of the number line lies in its ability to represent both positive and negative values. For the first time, we can see that numbers have not just a magnitude, but a direction. Positive numbers extend to the right, negative numbers to the left. This symmetry allows us to understand not just quantities, but relationships between them. The number line gives us a way to think about balance, motion, and change. The concept of negative numbers was met with resistance for centuries. For much of human history, the idea of having less than 0 was counterintuitive. After all, how could you have less of something when there was nothing to subtract from? Yet, through the gradual accumulation of knowledge, negative numbers gained acceptance. They began to be used to represent debt, temperatures below freezing, and other situations where a lack was just as real as a gain. One of the great breakthroughs that emerged from this new understanding of numbers was the creation of the coordinate plane. Imagine a second number line, this one running vertically. Now you have a two-dimensional grid, with each point on the grid defined by two numbers, one for the horizontal axis, the x-axis, and one for the vertical axis, the y-axis. With this simple addition, you now have a way to represent not just linear relationships, but geometric shapes, curves, and patterns. The coordinate plane, like the number line, is an abstraction. It represents the relationships between points in space rather than the space itself. But this abstraction is incredibly powerful. It allows us to map out everything from the path of a falling object to the orbits of planets. It is, in a sense, the language in which the universe is written. As we begin to plot points on the coordinate plane, we can see how geometry and algebra come together. The coordinate system allows us to describe shapes in terms of equations. A straight line, for example, can be represented by a linear equation, and its slope can be calculated by comparing the change in y values to the change in x values. A circle can be represented by an equation that describes all the points equal from a central point. In this way, algebra and geometry, once separate branches of mathematics, are fused into a single, cohesive language. In the same way that 0 anchored the number line, the coordinate plane allows us to anchor the entire concept of space and geometry by giving us a way to represent both points and relationships between points. The coordinate plane gives shape to the very concept of emptiness. The space between points on the grid may appear empty, but it is filled with meaning. Every point has a location, every relationship a pattern. The creation of the coordinate plane also opens up new possibilities for understanding motion. For example, the motion of a point across the plane can be described in terms of its x and y coordinates. As the point moves, it traces out a path that can be described mathematically. This ability to describe motion geometrically is not just a mathematical curiosity, it is a fundamental tool for understanding the physical world. But the coordinate plane doesn't just represent the world of everyday objects. It also allows us to explore more abstract concepts, like infinity and limits. The idea of a point that extends infinitely in all directions is central to modern physics, where we often think of the universe as an infinite, expanding space. The coordinate plane provides the tools to visualize these concepts and to think about the infinite in a structured way. From the coordinate plane, we move into more complex forms of geometry, such as three-dimensional space. Just as the number line describes one dimension and the coordinate plane describes two dimensions, we can extend these ideas into 3 dimensions and beyond. The concept of space, once an abstract idea, becomes something we can visualize, measure, and understand in terms of precise mathematical rules. In this way, the number line and coordinate plane are not just mathematical tools, they are models of the universe itself. They allow us to describe the world in ways that are both precise and intuitive. And as we continue to explore the nature of emptiness, space, and motion, these tools will become indispensable in helping us understand the universe on both the largest and smallest scales. The number line and coordinate plane also open the door to the concept of symmetry, which plays a central role in physics. In both the physical world and the mathematical world, symmetry allows us to predict how objects will behave. A sphere, for example, is symmetrical in all directions. It looks the same no matter how you rotate it. This symmetry can be described mathematically on the coordinate plane, where every point on the sphere is equidistant from the center. Symmetry, in this way, provides a kind of map for understanding the rules that govern the universe. As we continue to explore the empty spaces between points, we will see how this geometry, this map of relationships, becomes the foundation for understanding the forces of the universe. From the simplest equations to the complex motions of planets and stars, the coordinate plane gives structure to the emptiness between them. It is a reminder that even in the most seemingly empty spaces, there is a structure, a pattern, a relationship that can be understood and described. The language of geometry, born from the simplicity of the number line and the coordinate plane, is the language of the universe. It is the quiet order beneath the chaos, the calm that shapes the seemingly random motions of the cosmos. It is in this quiet order that we find the true nature of space, not as a blank, featureless void, but as a structured, meaningful place that can be measured, understood, and explored. As we trace the development of mathematical ideas, we arrive at a moment of profound transformation. The number line, once a simple structure for representing numbers, begins to take on an entirely new dimension. With the advent of calculus, mathematics moves from the realm of fixed numbers to a world of infinitely small quantities that approach zero but never quite reach it. This shift from the finite to the infinite is one of the most elegant and powerful ideas in the history of science, and it arises from a seemingly paradoxical concept. The limit, in the 17th century, to mathematicians Isaac Newton and Gottfried Wilhelm Leibniz independently developed the principles of calculus, which would forever change the way we understand motion, change, and the very nature of space itself. At the heart of calculus is the idea of a limit, the process of approaching a value without necessarily reaching it. To understand this concept, let's start with a simple question. What happens when we divide a number by something that gets closer and closer to 0? For example, consider dividing 1 by 10. The result is 0.1. Now, divide 1 by 1000. The result is 0.001. As the denominator shrinks, the result gets smaller and smaller. But what happens as the denominator approaches 0? The result grows without bound. It becomes infinitely large. This behavior, where a quantity increases or decreases without bound as it approaches a limit, is central to the concept of calculus. The key insight of calculus is that we can study these limits to understand the behavior of functions and shapes at the smallest possible scales. We no longer need to worry about exact values. Instead, we focus on the behavior of a function as it approaches a particular point, even if it never quite reaches it. This idea of approaching but never quite reaching 0, the limit, has profound implications for how we understand the universe. It is through limits that we can describe continuous change, the motion of objects, and even the flow of time itself. A moving object, for example, can never be at exactly 0 speed, but we can describe its velocity as it approaches 0. This ability to understand the infinitely small, to capture the essence of change without having to focus on the exact moments between states, opens up an entirely new way of thinking. Newton and Leibniz's work with limits allowed them to solve problems that had previously been intractable. They used calculus to describe the motion of planets, the trajectory of falling objects, and the flow of fluids. By understanding how things change continuously, calculus gave scientists the tools they needed to explain complex phenomena, from the motion of the Earth to the behavior of light and sound. The concept of a limit also introduces us to the idea of continuity, an important concept in both mathematics and physics. Continuity refers to the smooth, uninterrupted nature of a function or process. In the physical world, we see continuity in the way objects move. A ball doesn't suddenly jump from one position to another, but rather moves smoothly through space. Calculus allows us to describe this smoothness mathematically, understanding how the position of an object changes over time in a continuous manner. In the context of space and time, calculus gives us a tool to understand the universe as a continuous whole. Time is no longer a series of discrete moments, but a flowing, continuous process. Similarly, space is not just a collection of fixed points, but a dynamic and ever-changing field. The concept of limits allows us to describe the infinitesimal changes that occur at every moment, without ever needing to focus on the specific, finite values. Perhaps the most striking aspect of this approach to 0 and limits is the way it transcends the simple notion of nothingness. In classical philosophy, nothingness was often seen as an absence, an empty void. But in the world of calculus, 0 is not merely an absence, it is a threshold, a boundary that defines the behavior of the universe at its most fundamental level. For example, the derivative, one of the central concepts in calculus, describes how a function changes as we approach an infinitesimally small change in the input. In other words, it describes how a quantity evolves over time, even when that change is so small that it seems to be nothing. The derivative is a mathematical tool that captures the essence of change, even in the absence of observable movement. It shows us that even in the most infinitesimal changes, there is something happening, something that can be measured and understood. The concept of limits also provides the foundation for understanding the geometry of space at its smallest scales. When we approach zero, we enter a realm of infinitesimal measurements, distances that are so small they cannot be measured directly, but that have a profound impact on the way objects behave. In this world of the infinitely small, the laws of physics break down in fascinating ways. The concept of the limit, however, allows us to study these laws, even when they approach zero, providing a way to understand how objects move and interact. At the most fundamental levels, at the quantum level, for instance, the very concept of continuous change breaks down. Instead of smooth, continuous motion, particles behave in discrete steps. And yet, it is through the mathematics of calculus, with its emphasis on limits, that we can still make sense of these behaviors, describing how particles move and interact in ways that defy classical intuition. Calculus is not just a tool for understanding motion, however. It also provides a way to understand the very fabric of reality. The idea of limits extends beyond motion and space to the laws that govern the universe. Through the language of calculus, scientists have been able to describe the behavior of everything from the smallest subatomic particles to the largest galaxies, all by understanding how things change at their most fundamental level. This ability to work with the infinitely small, to study the behavior of things as they approach zero, reveals something profound about the nature of the universe. It shows us that even in the most seemingly insignificant moments, there is an underlying structure that can be understood and described. Nothingness, far from being empty and meaningless, is a wellspring of information and insight, holding the keys to the most profound mysteries of existence. As we continue to explore the nature of the void, we will see how the concept of limits plays a crucial role in understanding the strange and fascinating world of quantum mechanics, where the behavior of particles and forces is governed by probabilities and uncertainties. But before we leave the realm of calculus behind, let us remember that the concept of limits is not just a mathematical tool, it is a window into the very nature of reality itself. As we step further into the journey of understanding nothingness and the infinite, we encounter a quiet yet profound shift in how we perceive space, form, and the nature of reality itself. The path forward is marked by one of the most important turning points in geometry, the exploration of Euclid's work and the emergence of a new, systematic way of seeing the world. It's here, in the foundational garden of geometry, that the seeds of future scientific revolution are planted. Euclid, often called the father of geometry, presented his system of thought in his famous work Elements, a text that would dominate mathematics for over 2 millennia. Euclid's approach was groundbreaking because it shifted our perception of space from something intuitive and irregular to something measurable, logical, and precise. His axioms were simple, but they laid the groundwork for all future geometry. And mathematics, at the heart of Euclidean geometry, is the idea that space itself is a vast, interconnected structure governed by rules and relationships. Every point, every line, and every angle fits within a set of principles that define how they interact. But for Euclid, this system was not just about shapes and figures. It was about the essence of reality. By abstracting space into a set of principles, Euclid created a lens through which all phenomena, both physical and theoretical, could be understood and described. Euclid's most famous postulate, perhaps, is the parallel postulate, which states that through any point, not on a given line, there is exactly one line parallel to the original line. For centuries, mathematicians tried to prove or disprove this postulate, because if it were wrong, the very structure of geometry could change. For the longest time, the parallel postulate seemed self-evident and irrefutable. However, as mathematical inquiry advanced, it became clear that this seemingly simple assumption was far from innocuous. Euclid's geometry had a quiet, serene quality to it. It was a world of clarity, where shapes were drawn and measured with perfect precision. Yet, within this seemingly ordered world, a deeper mystery was beginning to stir, one that would unravel the assumptions upon which Euclid's geometry was built. In the 19th century, mathematicians such as Carl Friedrich Gauss, Nikolai Lobachevsky, and Janos Bollier discovered something extraordinary. What would happen if you rejected the parallel postulate altogether? What if, instead of one parallel line, there were infinitely many, or none at all? This idea gave rise to non-Euclidean geometries, spherical and hyperbolic geometry, where the parallel postulate no longer held true. In spherical geometry, for example, there are no parallel lines because all lines eventually intersect. This might seem strange, but it is precisely how the surface of a sphere works. Think of the lines of longitude on Earth, which all meet at the poles. This realization would eventually transform our understanding of space, leading directly to Albert Einstein's theory of general relativity, where space itself was not flat and unchanging, but curved and dynamic, just like the surface of a sphere. On the other hand, hyperbolic geometry, which was first described by Lobachevsky, opened the door to a world where the geometry of space had an entirely different structure. In this model, through any point, there are infinitely many lines parallel to a given line. This idea was radical at the time because it suggested a space that was not flat, but bent and folded upon itself in a way that was previously unimaginable. The implications of non-Euclidean geometry were vast. They showed that the assumptions we take for granted, like the nature of parallel lines, were not absolute. Space, it turns out, is not a rigid, unchanging stage, but a flexible, malleable concept. The geometric world Euclid created was not the only possible world, and the quiet beauty of his axioms was challenged by the discovery of other equally valid geometries. This revelation, the recognition that the rules of geometry could change, depending on the assumptions we make about space, had profound consequences. It was a dramatic shift in how we understood the universe. For centuries, mathematicians had viewed Euclidean geometry as a complete, self-contained system, but now they realized that the very nature of space itself could be altered and different. Geometries could exist in parallel. The discovery of non-Euclidean geometry marked the beginning of a new era of mathematical thought. It showed that geometry, once thought to be an immutable truth, was actually a dynamic and evolving field. This opened up new ways of thinking about the universe and about the very fabric of reality itself. But there was still more to come. Just as Euclid had created the quiet, orderly garden of geometry, the world of mathematics would soon blossom into an even more abstract, more complex domain. The exploration of non-Euclidean geometries would eventually lead to the realization that the very structure of space was not only curved in certain circumstances, but that space itself could be affected by gravity, time, and energy, as we progress. In this exploration of space and emptiness, we will see how these abstract mathematical ideas gave birth to an entirely new view of the universe, one in which space itself is not a passive backdrop to the events of the cosmos, but an active participant in the unfolding drama of existence. The quiet garden of Euclidean geometry, once thought to be the foundation of all mathematics, was just the beginning. As new geometries emerged, so too did new ways of thinking about the very shape of the universe. The ideas that began with Euclid Ideas about points, lines, and planes would eventually lead to the understanding that the universe itself was not just a collection of objects, but a vast, interconnected web of relationships. Geometry, once the realm of abstract shapes and idealized forms, became the language of the cosmos, describing everything from the smallest particles to the largest galaxies. And as we will see in the next chapters, these ideas will play a central role in the greatest discoveries of modern physics, discoveries that have revolutionized our understanding of time, space, and the very nature of nothingness itself. At the heart of Euclid's geometry lies one seemingly simple assumption, the parallel postulate. This postulate, which states that through any point not on a given line, there is exactly one line parallel to the original line, formed the bedrock of classical geometry. For over 2,000 years, it was taken for granted that this postulate described the very nature of space itself. It was the fundamental rule that governed how we understood lines, angles, and the relationships between points in space. But what if this postulate weren't true? What if, instead of one parallel line, there were many or none at all? What if the very fabric of space itself didn't adhere to the rules that Euclid had established? These seemingly simple questions, when posed in the 19th century, led to one of the most profound revolutions in mathematics. The discovery of non-Euclidean geometries, the realization that the parallel postulate could be false, marked a major turning point in our understanding of geometry and, ultimately, of the very nature of space itself. The idea of parallel lines had been a cornerstone of classical geometry, but as mathematicians began to question this assumption, they opened the door to new possibilities that would reshape the very way we think about the universe. The discovery of non-Euclidean geometry was the work of several brilliant minds, but the primary contributors were Carl Friedrich Gauss, Nikolai Lobachevsky, and Janos Bolyai. Gauss, often regarded as one of the greatest mathematicians in history, was the first to glimpse the possibility that the parallel postulate might not hold in certain cases. Though he didn't publish his findings, his ideas influenced later mathematicians, including Lobachevsky and Bolyai, who independently developed the principles of hyperbolic geometry, a form of non-Euclidean geometry where the parallel postulate does not apply. In hyperbolic geometry, parallel lines do not behave as they do in Euclidean space. Instead of one parallel line passing through a point, there are infinitely many lines that do not intersect the original line. This leads to a radically different understanding of space, a space that is not flat, but curved. The world of hyperbolic geometry is a world where straight lines are not straight in the traditional sense. Instead, they bend and curve, forming a network of interwoven paths. But it wasn't just hyperbolic geometry that emerged from this challenge to Euclid's postulate. In spherical geometry, the parallel postulate also breaks down. On the surface of a sphere, for example, there are no parallel lines. Every line eventually intersects another. The lines of longitude on the Earth's surface, which might seem parallel at the equator, converge at the poles. In this space, the very concept of parallelism is meaningless. Instead of an infinite, flat plane, space takes on the shape of a curved surface, and the geometry of that surface is fundamentally different from the geometry of a flat plane. These discoveries were not just academic curiosities. They had profound implications for the way we understand the universe. The realization that space could have different geometries, curved, warped, or even hyperbolic, challenged the very idea that Euclidean geometry described the true nature of the cosmos. What if the universe itself, instead of being flat and uniform, was curved in some way? What if, like the surface of a sphere, space was not infinite and unchanging, but curved and dynamic. This insight would eventually lead to the theory of general relativity, proposed by Albert Einstein in the early 20th century. In Einstein's view, space and time are not separate, fixed entities, but are intertwined in a four-dimensional fabric, known as spacetime. Just as the surface of a sphere is curved, so too is spacetime curved by the presence of mass and energy. In this new framework, the parallel postulate no longer applies because the very structure of space itself is not flat. Objects move along curved paths, dictated by the curvature of spacetime, and these paths are influenced by the distribution of mass and energy. Einstein's theory was groundbreaking, because it showed that the geometry of the universe was not something static and unchanging, as Euclid had imagined, but something dynamic and malleable. Space itself could be warped and stretched, depending on the mass of objects within it. The idea that space could curve and bend in response to gravity was a direct result of the discoveries made by mathematicians working with non-Euclidean geometry. But, even as Einstein's ideas were taking shape, the implications of non-Euclidean geometry were still being explored by mathematicians and physicists alike. The idea that the geometry of space could be different from the familiar Euclidean space opened up a new world of possibilities. It was a world where straight lines could curve, where parallel lines could diverge, and where the very structure of the cosmos could be shaped by the forces of gravity and motion at the same time. The discovery of non-Euclidean geometry challenged the long-standing belief that Euclidean geometry was the only valid form of geometry. Once thought to be the true, absolute description of space, Euclidean geometry was now just one of many possible ways to describe the relationships between points, lines, and planes. The understanding that there were other geometries, each with its own set of rules and principles, shattered the illusion of Euclidean geometry as the one true system. The parallel postulate, once regarded as a simple, self-evident truth, had turned out to be fragile. In its place, a new understanding of space emerged, one in which the structure of the universe was not fixed and immutable, but subject to change and curvature. The discoveries of non-Euclidean geometry opened the door to a new way of thinking about space, time, and the very nature of the universe. As we continue to explore the consequences of these mathematical revelations, we will see how they laid the groundwork for some of the most profound discoveries in modern physics. From the bending of light around stars to the expansion of the universe itself, the insights gained from non-Euclidean geometry continue to shape our understanding of the cosmos. The once fragile postulate that defined Euclidean geometry has given way to a more flexible, dynamic view of space, a view in which the very fabric of reality is not fixed, but constantly shifting and evolving. As we move deeper into the unfolding narrative of space and geometry, the implications of non-Euclidean geometry begin to resonate with greater power. It's no longer enough to simply imagine a world where parallel lines diverge or converge. We must now confront the idea that the very fabric of the universe itself may not be flat, but curved in ways we've only begun to understand. The world of curved spaces, once a theoretical abstraction, has now become a fundamental piece of our understanding of reality, one that stretches beyond the purely mathematical into the realms of physics, astronomy, and cosmology. For centuries, space had been thought of as an infinite, flat expanse, an empty, featureless void in which objects and bodies moved according to predictable laws. But the discoveries of non-Euclidean geometry, especially the idea that space could curve, shattered This simple picture, curved space or curved geometry, suggested that the very nature of the universe could be radically different from what was previously imagined. The most striking example of curved space in practice is the shape of the Earth. For centuries, people believed the world was flat, a simple plane on which we lived and walked. Yet, as explorers sailed further across the oceans, they realized that the Earth was round and that its surface could be described using spherical geometry. This realization that space could be curved in a way that was more complex than simple. Euclidean geometry was the first crack in the once stable foundation of our spatial understanding. But spherical geometry, though revolutionary in its own right, was just the beginning. The true implications of curved space would only be fully realized with the advent of Einstein's theory of general relativity. As we saw earlier, general relativity does away with the idea of flat, static space and replaces it with a dynamic, curved spacetime that responds to the presence of mass and energy. In Einstein's view, space and time were not separate entities. They were intertwined in a single, four-dimensional fabric that could bend and warp depending on the objects within it. What does it mean for space to be curved? To understand this, imagine the surface of a trampoline. If you place a heavy object, such as a bowling ball, in the center of the trampoline, the fabric bends and curves around it. The more massive the object, the greater the curvature. Similarly, in Einstein's view, massive objects like planets and stars curve the fabric of spacetime, causing the paths of objects that pass nearby to bend. This effect, which we perceive as gravity, is not the result of an invisible force pulling objects toward one another, as Newton once thought, but rather the result of the curvature of spacetime itself. This idea was revolutionary, and it marked a fundamental shift in our understanding of the universe. The notion that space itself could bend in response to the presence of matter was an idea that had emerged from the world of abstract mathematics, but it was now being applied to the real world. It explained why planets orbited the sun, why light bent around massive objects, and even why the universe itself was expanding. To visualize this curvature of space, we can turn to a simple analogy. Imagine a two-dimensional being living on a flat surface, perhaps a piece of paper. This being would have no concept of up or down. It could only move in two directions, along the surface of the paper. Now, imagine that this being encounters a curve, a bend in the paper. The being would perceive the world around it to be distorted, as if the very fabric of its universe had changed. In a similar way, we, as three-dimensional beings, experience the curvature of space as the bending of light, the motion of objects, and the warping of time. But what happens when we move beyond simple curvature to a universe of even greater complexity? As scientists began to explore the implications of general relativity, they realized that the universe itself could be thought of as a kind of cosmic fabric, a malleable, ever-changing structure in which space and time are woven together. This realization led to a host of new questions. What happens to the geometry of space when there is more mass? How does the curvature of spacetime affect the paths of light? Can the geometry of space explain the mysterious force of gravity? The answers to these questions would begin to emerge as astronomers and physicists delved deeper into the fabric of the universe. One of the most stunning revelations came in 1919, when a team of astronomers, led by Arthur Eddington, confirmed a prediction made by Einstein. They observed the bending of light around the sun during a total solar eclipse. The results of their observations showed that light, which was once thought to travel in straight lines, could, in fact, be bent by the curvature of space. This was the first direct observation of the curvature of spacetime, and it provided powerful evidence in favor of Einstein's theory. The implications of curved space were not limited to the behavior of light or the paths of planets. As physicists began to explore the geometry of space on larger scales, they discovered that the entire universe might be curved. This idea, which would later be developed into the theory of cosmic inflation, suggests that the universe itself could be finite, yet unbounded like the surface of a sphere. If space is curved in this way, it could explain the observed expansion of the universe. Instead of expanding outward into an empty void, the universe may be expanding along the curved surface of its own space. Curved space also led to new insights into the nature of black holes, those mysterious regions of space where gravity is so intense that nothing, not even light, can escape. The discovery of black holes confirmed that the curvature of space-time could become extreme, creating regions where time itself seemed to slow down or stop altogether. The event horizon of a black hole, the point beyond which nothing can escape, is a boundary between different regions of curved space. Inside the event horizon, space and time become so warped that the normal rules of physics no longer apply. These discoveries continue to challenge our understanding of space and time. In some ways, curved space is still an abstract concept, an idea that we describe mathematically, but that we can't directly observe. Yet, the consequences of curved space are all around us, from the orbits of planets to the bending of light. The very fabric of our universe is shaped by the curvature of space itself. As we continue our exploration of the void and nothingness, we find that space is not an empty stage on which events unfold. It is a dynamic, malleable entity, curved, bent, and shaped by the objects within it. The quiet, steady beauty of geometry, once defined by Euclid's axioms, has given way to a new, dynamic understanding of the universe, one where space itself is not just a passive backdrop but an active participant in the unfolding drama of existence. As we venture further into the landscape of curved spaces and non-Euclidean geometry, we begin to encounter a world of abstraction that is both fascinating and disorienting. The concept of hyperbolic space, introduced by mathematicians like Lobachevsky and Beaulier, stretches our imagination and challenges the very nature of geometry as we know it. To help us understand this strange new world, we must move beyond the intuitive, flat Euclidean geometry we're familiar with, and learn to visualize a space where parallel lines don't behave as we expect, where the very rules of geometry are altered in profound ways. Hyperbolic space is often described as a negatively curved geometry. Unlike the positive curvature of a sphere, where lines eventually converge, or Euclidean space, where parallel lines never meet, hyperbolic geometry takes a radically different approach. In hyperbolic space, the angles of a triangle add up to less than 180 degrees, and the lines that should be parallel according to Euclidean rules can diverge endlessly. In essence, hyperbolic space is a universe that defies our usual rules for distance and angles, a space where the normal geometric principles we've come to rely on no longer hold. One of the most useful ways to visualize hyperbolic space is to consider the Poincare disk model. In this model, the entire hyperbolic plane is represented inside a circle, while the interior of the circle appears to be flat. As you move closer to the edge, the geometry becomes increasingly distorted. Lines in the Poincare model are actually arcs of circles that bend toward the boundary of the disk, and parallel lines that begin as straight lines inside the disk will diverge as they approach the edge. This visual representation allows us to see how space can bend and stretch in unexpected ways, but it also challenges our traditional understanding of what it means for lines to be parallel or for space to be flat. In the Poincare disk model, distances are measured not by the straight lines we're used to, but by curves that bend through the interior of the disk. The further you move from the center, the more the space itself seems to expand, and the less the familiar rules of Euclidean geometry apply. This subtle yet profound shift in how we think about space is a powerful reminder that our intuitions about geometry shaped by the flats. Everyday world may not always be reliable when applied to spaces of more complex curvature. Another way to visualize hyperbolic space is through the use of the upper half-plane model, which also represents hyperbolic space on a two-dimensional surface. In this model, the geometry of the space is mapped onto a half-plane, with lines represented by vertical lines and semicircles. Just as in the Poincare disk, the geometry of this space is radically different from the Euclidean plane. Angles and distances behave in ways that are unfamiliar, and the very idea of distance itself becomes more fluid, more relative. The world inside this space is one where straight lines are no longer the simplest path between 2 points, and where the space between objects behaves unpredictably, depending on the context in which it is observed. While hyperbolic space might seem like a strange abstraction, its implications are far-reaching, particularly in the fields of mathematics and physics. It offers a radically different way of thinking about space, one that could provide insight into the shape of the universe itself. In the 20th century, as scientists began to explore the large-scale structure of the cosmos, the possibility that the universe might be curved in a hyperbolic manner became a real question. If space itself is curved, could it be that the universe is not an infinite, flat expanse, but instead a vast, negatively curved space? Could the universe itself be modeled by the very principles that govern hyperbolic geometry? This question of curvature took on even greater importance with the development of cosmological theories in the 20th century. With Einstein's theory of general relativity and the expanding universe model developed by Edwin Hubble and others, scientists began to ask whether the curvature of space could explain the observed expansion of the cosmos. If space were curved, this might explain why the universe appears to be stretching out in all directions, how the galaxies seem to be moving away from us, not just locally, but universally. This idea that space itself could have a hyperbolic geometry helped lead to the development of models of cosmic inflation, where the universe rapidly expanded in the moments after the Big Bang. Moreover, hyperbolic geometry has applications beyond cosmology and general relativity. It plays an important role in the study of complex networks, such as the Internet or social media, where the relationships between nodes, websites, users, or data points form patterns that are naturally described by hyperbolic geometry. These networks often exhibit properties similar to those of hyperbolic space, where the relationships between nodes can be represented in a way that transcends the simple Euclidean geometry we use to map our everyday world. Additionally, hyperbolic geometry has found applications in the study of dynamical systems, particularly in areas like fluid dynamics, where the behavior of particles or molecules in a turbulent flow can be described using the principles of curved space. The idea that physical systems, at a deep level, may follow patterns of behavior that are best understood in terms of non-Euclidean Geometry opens up entirely new avenues for scientific exploration, but it's not just in mathematics and physics that hyperbolic space finds relevance. It has profound implications for the way we think about the nature of space itself. In Euclidean geometry, we are accustomed to thinking of space as a flat, infinite plane, where distances between objects are predictable and regular. Hyperbolic geometry, however, shows us that space can be radically different, that the relationships between objects can be far more complex and unpredictable. This shift in perspective challenges our deeply held assumptions about the structure of the world and forces us to reconsider the very nature of reality. In a way, hyperbolic space offers us a glimpse into the possibilities that lie beyond the familiar world of Euclidean geometry. It invites us to imagine a universe where space itself is not flat but curved, where the very rules we rely on for understanding distance, angles, and motion must be rewritten. In this world, the geometry of space is not fixed. It is dynamic, ever-changing, and infinitely complex. And as we continue to explore the implications of curved spaces, we begin to see how these mathematical models of hyperbolic geometry and other non-Euclidean systems can help us understand everything from the behavior of light in a gravitational field to the large-scale structure of the cosmos. The journey of understanding nothingness and the nature of space has just begun, and as we move deeper into the fabric of reality, we will see that the seemingly simple concepts of geometry have profound and far-reaching consequences for how we understand the universe. As we continue our journey through the abstract world of geometry, we encounter a striking intersection between mathematical theory and the tangible world around us. Hyperbolic geometry, with its strange and counterintuitive properties, may have once seemed like a distant curiosity, far removed from practical concerns. But as we delve deeper into the intricacies of mapping and measurement, we begin to see how this abstract geometry takes on profound real-world significance. In fact, the very fabric of our daily experience is shaped by these mathematical ideas. The world, as we experience it, is not flat. This simple observation, now a fundamental part of our understanding of geography and physics, was once a radical idea. The ancient Greeks, for example, believed that the earth was flat, as did most other cultures throughout history. It wasn't until the Greeks developed their understanding of spherical geometry, with figures like Pythagoras and Aristotle leading the way, that the true shape of our planet began to be understood. One of the first clues that the earth was not flat came from the study of the stars. Observations from different parts of the world showed that the stars appeared to shift position as one moved further north or south. This shifting of the stars could only be explained by the curvature of the Earth's surface. The idea of a spherical Earth, however, did not take hold immediately. It wasn't until the work of Eratosthenes in the 3rd century BCE that the size of the Earth was measured with remarkable accuracy using the principles of geometry. Eratosthenes, a Greek mathematician, used the differences in the angles of the sun's rays at 2 different locations to calculate the circumference of the Earth. He knew that at noon on the summer solstice, the sun would be directly overhead in the Egyptian city of Syene, but at the same time in Alexandria, the sun would cast a small shadow. By measuring the angle of the shadow and knowing the distance between the 2 cities, Eratosthenes was able to calculate the Earth's circumference with surprising accuracy within about 2% of the true value. This achievement, while a breakthrough in its time, was only the beginning. As exploration and navigation advanced, the need to accurately map the Earth and understand its shape became even more pressing. In the 16th century, the rise of global exploration brought with it the challenge of representing the curved surface of the Earth on a flat map. This challenge of translating the 3D curvature of the Earth into 2D representations would inspire some of the most important advancements in the field of cartography and map-making. The most famous method of creating flat maps from a spherical surface is the Mercator projection, developed by the Flemish cartographer Gerardus Mercator in 1569. This projection is still used today in many types of maps, particularly for nautical navigation. The Mercator projection distorts the Earth's surface in a way that makes straight lines, or rhumb lines, appear as straight lines on the map, making it easier to plot courses across the globe. While this projection is incredibly useful for navigation, it comes with significant distortions, especially near the poles, where areas appear much larger than they actually are. This is where the connection between hyperbolic geometry and the real world becomes clearer. The Mercator projection, with its distortions, is a reminder that the surface of the Earth is not flat, it is curved. The very act of mapping a curved surface onto a flat surface involves complex mathematical transformations, while the Mercator projection makes some compromises to preserve navigational accuracy. It cannot fully account for the curvature of the Earth in a way that perfectly represents the true shape of the planet. The challenge of accurately representing a curved space was not limited to the Earth. As astronomers turned their gaze toward the heavens, they realized that the same principles of geometry applied to the cosmos as well. The curvature of space, as described by Einstein's theory of general relativity, showed that the universe itself could be understood in terms of curved geometry. This idea, once abstract and theoretical, began to take on a more tangible form. As scientists realized that the very structure of the cosmos was shaped by the geometry of space itself, the discovery that space is curved and that the Earth is not flat has profound implications for our understanding of the universe. It forces us to confront the idea that the world we live in is not as simple as it may seem. From the surface of our planet to the farthest reaches of the universe, space is a dynamic, ever-changing entity that cannot be fully understood through the lens of flats. Euclidean geometry alone, the curvature of space, once a theoretical curiosity, explored by mathematicians, has become central to our understanding of the universe. In a sense, maps have become not just representations of the Earth, but models of the very fabric of reality itself. The same principles that govern the curvature of the Earth govern the curvature of space, and by understanding these principles, we can gain deeper insight into the structure and evolution of the cosmos. But the journey from maps to reality doesn't end with the Earth's surface. The exploration of the universe itself, from the solar system to distant galaxies, continues to rely on the principles of geometry. And as our understanding of the cosmos deepens, so too does our understanding of the fundamental shape of space. Whether through the use of astronomical observations or the study of the cosmic microwave background, we are slowly piecing together the puzzle of the universe's curvature. This journey from the first understanding of the Earth's spherical shape to the modern realization that space itself is curved reveals something profound about our relationship to the universe. The maps we create, whether of our planet or the cosmos, are not just representations. They are reflections of our evolving understanding of space itself. Just as Euclid's geometry gave us the tools to measure and understand space, the modern study of curved space gives us a new framework for understanding the very fabric of reality. In the next chapters, we will continue to explore the implications of this new geometry, delving into how these mathematical principles are used to understand everything from the orbits of planets to the behavior of light and time. The journey through the universe is not just a journey through space, it is a journey through the very structure of reality, where maps and models reflect not only the shape of the world, but the underlying principles that govern all existence. As we move deeper into the study of space, curvature, and geometry, we come to an idea that has become central to modern physics and mathematics, the concept of the manifold. A manifold is a mathematical space that, on a small scale, resembles flat Euclidean space, but on a large scale can exhibit complex curvature and structure. This idea, while initially abstract, serves as the foundation for understanding the very fabric of the universe itself. The concept of a manifold arises from the need to describe spaces that are not necessarily flat or easy to understand, while Euclidean geometry works well for describing flat, three-dimensional spaces like the room you are sitting in. It falls short when we try to describe more complex, curved spaces like the surface of a sphere or the curved spacetime described by Einstein's theory of general relativity. Manifolds provide a way to generalize the idea of space, allowing us to describe spaces that are both curved and complex, yet locally behave as if they were flat. In simple terms, a manifold is a space made up of smaller, flat regions, much like the way the Earth is composed of small, flat patches of land that, when viewed from a larger perspective, curve into a spherical shape. Manifolds allow us to describe complex shapes and surfaces that would otherwise be impossible to capture with the traditional, flat geometry of Euclid. The concept of a manifold is most famously applied in the theory of general relativity. In Einstein's view, space and time are not separate, fixed entities but are part of a unified four-dimensional fabric called spacetime. This fabric, which encompasses both space and time, is curved by the presence of mass and energy. The presence of large objects like stars and planets distorts spacetime, creating what we perceive as gravity. This curvature of spacetime can be thought of as a manifold, locally flat in small regions, but globally curved by the distribution of mass and energy. In this context, the manifold is more than just a mathematical abstraction. It provides a framework for understanding the very structure of the universe. When we think about gravity in Einstein's theory, we are actually thinking about the way mass curves the space-time manifold. Objects, like planets and stars, move along the paths dictated by this curvature, and the curvature itself is determined by the distribution of mass and energy throughout the universe. The idea of a manifold allows us to visualize the universe as something much more flexible and dynamic than we once imagined. It's not just a collection of objects moving through a static space. It's a complex, interconnected structure, constantly shifting and warping in response to the mass and energy that populate it. Just as the surface of a balloon can be deformed by the air inside it, space-time can be warped and stretched by the presence of mass. This idea has profound implications for our understanding of the universe. It tells us that space is not a simple, static stage upon which events unfold. It is an active, dynamic entity that interacts with the objects within it. The curvature of spacetime is not just an abstract concept. It governs the motion of planets, the path of light, and the flow of time itself. Manifolds also have applications far beyond the realm of general relativity. In mathematics, they are used to describe the shape of complex spaces in a wide variety of fields, from topology to geometry to theoretical physics. The study of manifolds is central to understanding the geometry of the universe, the behavior of quantum fields, and the structure of fundamental forces like gravity and electromagnetism. One of the most exciting applications of manifold theory is in the study of string theory. A leading candidate for a theory of everything, a unified framework that describes all the fundamental forces of nature. In string theory, the universe is described not by point-like particles, but by tiny, vibrating strings. These strings exist in a higher dimensional space, a manifold, and their vibrations give rise to the particles and forces we observe. The study of manifolds is central to understanding the higher dimensional spaces that string theory posits, and it provides a framework for describing the fundamental nature of reality at its most basic level. Manifolds also play a crucial role in our understanding of the shape of the universe. Just as we can describe the surface of a sphere as a manifold, we can also describe the entire universe as a manifold, whose curvature is determined by the distribution of matter and energy. The shape of the universe itself, whether it is flat, spherical, or hyperbolic, can be understood as a large-scale property of the spacetime manifold. This is one of the central questions in cosmology. What is the overall shape of the universe? Is it finite or infinite? Is it closed like a sphere or open like a saddle? These questions are not just abstract, they have real implications for how we understand the origin, evolution, and fate of the universe. The curvature of space and time determines the way galaxies move, the path of light, and the rate at which the universe is expanding. Understanding the manifold nature of spacetime is key to understanding the evolution of the cosmos itself. In many ways, the idea of a manifold brings us back to the very foundations of geometry. Just as Euclid's geometry helped us understand the flat, static world around us, the concept of manifolds helps us navigate the dynamic, curved universe. It provides a way to describe spaces that are too complex to fit into the rigid confines of Euclidean geometry, offering a flexible, powerful framework for understanding the universe in all its curvature and complexity. The study of manifolds is not just a mathematical pursuit, it is a key to unlocking the deepest mysteries of the cosmos. By understanding how space is structured and how it bends and twists in response to the objects within it, we come closer to understanding the true nature of the universe. The fabric of space, woven from the threads of geometry, reveals the structure of reality itself, offering new insights into the forces that shape our world and our universe. As we continue our exploration of the mysteries of space, we will see how the manifold idea provides the foundation for understanding some of the most intriguing phenomena in modern physics. From black holes to the origins of the universe itself, the journey through the manifold is far from over, and it will continue to offer profound insights into the very nature of reality. As we begin to expand our exploration of the universe's geometric and mathematical properties, we move from the abstract world of curvature and manifolds into an area of mathematics that offers a new lens through which to view space itself. Topology, whereas geometry focuses on the precise measurement of shapes and spaces, topology concerns itself with the properties of space that remain unchanged under continuous deformation. In a sense, topology allows us to understand the deep structure of space, the features that are invariant regardless of how the space is stretched, twisted, or bent. To understand topology, let's first consider a simple question. What happens if you stretch a rubber band? As you pull on the rubber band, you can elongate it, distort it, and change its shape in numerous ways. However, despite these changes, the rubber band remains fundamentally the same, it's still a loop. The key idea in topology is that some properties of space, like being connected or having a hole, do not depend on exact measurements, but on the fundamental shape of the space. Even if it's been distorted, topology is often summed up by the phrase, "It's not about how things are shaped, but about how things are connected." For instance, a circle and an ellipse may appear different in size or elongation, but they are considered topologically equivalent because you can stretch one into the other without tearing or gluing. Similarly, a donut and a coffee cup are topologically equivalent because they both have a single hole, one for the handle of the cup, and one in the donut center. This concept of topology, the study of objects through their connectedness, has profound implications, not just in mathematics, but in understanding the very structure of the universe. In the realm of cosmology, topology can help us consider the possibility of a finite yet unbounded universe. In other words, could the universe be finite in size, yet without an edge or boundary? If the universe is topologically equivalent to a three-dimensional sphere, it could be finite, but it would have no edges or limits. In such a space, you could theoretically travel in one direction indefinitely and end up back where you started, much like traveling in a straight line across the surface of the Earth. This idea of a finite, unbounded universe is part of a fascinating philosophical and scientific question. Is the universe closed or open? Theories about the shape and structure of the universe, from Einstein's general relativity to modern cosmology, propose that the shape of space could be a direct result of the distribution of mass and energy. If the universe were closed, it could be analogous to the surface of a sphere, where space is finite but has no boundary. An open universe, on the other hand, might be analogous to a saddle, where space stretches out infinitely and has negative curvature. The true topology of the universe is a key area of ongoing research, with astronomers studying the cosmic microwave background and galaxy distributions to determine whether our universe is finite or infinite in a topological sense. Topology also plays a critical role in the study of black holes and other cosmic phenomena. Black holes, those regions of space where gravity is so intense that not even light can escape, have been described as creating holes in spacetime. These holes are not physical voids in the traditional sense, but rather areas where the curvature of spacetime becomes so extreme that the normal rules of physics break down. Understanding the topology of spacetime helps scientists conceptualize how such extreme curvatures affect the flow of time and space, providing insight into the behavior of objects near black holes. One of the most exciting applications of topology in physics is in the study of topological defects in materials, which can also be thought of as loops in spacetime. These defects, such as cosmic strings or monopoles, are hypothetical objects that could form when the universe underwent phase transitions during its early moments. They represent singularities in the fabric of spacetime, much like how a twist in a rubber band would create a topological defect. While these objects have yet to be observed directly, their theoretical implications suggest they could play a role in the formation of large-scale cosmic structures and in understanding the evolution of the universe itself. In quantum physics, topology also has a profound connection to the behavior of subatomic particles. The study of quantum field theory has led to the concept of topological quantum states, where particles behave in a way that is deeply influenced by the topology of the space they inhabit. For instance, topologically protected states are immune to small disturbances, much like a knot in a rope that stays intact despite being pulled and twisted. These states are at the forefront of quantum computing, offering a potential route to more stable, fault-tolerant quantum systems. Topology, in its simplest form, is about understanding how objects are connected to one another, whether they are loops, holes, or more complex shapes. But as we explore the universe, we begin to realize that this seemingly abstract field has profound implications for understanding everything from the large-scale structure of the cosmos to the microscopic behavior of quantum particles. The topological properties of space give us insight into the universe's most fundamental characteristics, whether it's the way light bends around a black hole or the way particles interact in a quantum system. The connection between topology and the universe is a reminder that reality is not simply a collection of discrete objects and phenomena, but a complex, interconnected web of relationships. Space itself is not simply a backdrop on which events unfold. It is a living, breathing entity that bends, twists, and connects everything in the universe. From the cosmic scale to the quantum level, topology gives us the tools to understand the invisible connections that bind the universe together. As we move forward in this exploration of the nature of space and nothingness, we will continue to see how these deep mathematical concepts, geometry, topology, and the curvature of space, help us understand the structure of the universe. Whether it's understanding the fate of black holes, exploring the behavior of quantum particles, or imagining the true shape of the cosmos, topology provides a powerful framework for understanding the universe's most elusive and fundamental aspects. As we continue to unravel the deep structure of the universe, we turn our attention to the most distant echoes of space itself. Light, the messenger that carries information from the farthest reaches of the cosmos, has long been a crucial tool in our quest to understand the shape of the universe. The study of light, how it travels, and how it bends, has provided us with a window into the curvature of space and the very nature of the cosmos. One of the most profound discoveries of the 20th century was the realization that light doesn't travel in straight lines, as we once assumed. Instead, light follows the curvature of space, bending as it passes near massive objects. This phenomenon, predicted by Albert Einstein in his theory of general relativity, was confirmed in 1919 during a solar eclipse. Astronomer Arthur Eddington led an expedition to observe the bending of starlight around the sun, and their observations confirmed Einstein's prediction. This discovery not only validated the idea that space is curved by the presence of mass, but also provided the first direct evidence that space itself is not a flat, static entity, but a dynamic, curving structure. The bending of light, known as gravitational lensing, has become one of the most important tools in modern astronomy. When light passes near a massive object, such as a galaxy or a cluster of galaxies, the curvature of space bends the light's path, causing distant objects to appear distorted or magnified. This effect allows astronomers to study objects that would otherwise be too distant or faint to observe, providing a cosmic magnifying glass through which we can peer into the distant past. Gravitational lensing has become a key tool in the study of dark matter, that mysterious substance that makes up most of the mass in the universe but remains invisible to direct observation. When light from a distant galaxy passes through a galaxy cluster, the mass of the cluster bends the light in a way that reveals the presence of unseen mass. By studying how light is bent in this way, scientists have been able to map out the distribution of dark matter across the universe, providing some of the most compelling evidence for its existence. But light doesn't just reveal the curvature of space near massive objects. It also gives us insight into the large-scale structure of the universe itself. One of the most exciting discoveries of modern cosmology has been the detection of the cosmic microwave background, CMB radiation. The faint afterglow of the Big Bang, this radiation, which fills the entire universe, provides a snapshot of the universe as it was just 380,000 years after its formation. By studying the tiny variations in temperature and density in the CMB, scientists have been able to map out the structure of the universe on the largest scales and determine its overall shape. The CMB provides a wealth of information about the geometry of the universe. By analyzing the patterns in the CMB, cosmologists have been able to determine that the universe is flat, meaning that the angles of triangles in the universe add up to 180 degrees, just like in Euclidean geometry. This finding suggests that the universe, on the largest scales, is close to being geometrically flat, which has profound implications for our understanding of the universe's fate. If the universe is flat, it will continue to expand forever, though at an ever-decreasing rate. If it were curved, it might eventually contract or reach a stable size. But while the CMB has provided evidence for a flat universe, it has also revealed something unexpected: tiny fluctuations in temperature that indicate that the universe is not completely homogeneous. These fluctuations, or clumps of matter, are the seeds of all structure in the universe, galaxies, stars, planets, and even us. The presence of these fluctuations tells us that the universe began with small, random variations that eventually grew into the complex web of galaxies and clusters we see today. In addition to the CMB, the study of light from distant galaxies has revealed another fascinating property of the universe: its expansion. In the 1920s, Edwin Hubble observed that galaxies were moving away from us, and the further away they were, the faster they seemed to be receding. This discovery, now known as Hubble's law, provided the first evidence that the universe is expanding. The light from these galaxies was redshifted, meaning that the wavelengths of the light were stretched as the galaxies moved away from us. This redshift is a direct consequence of the expansion of space itself, and it has allowed us to measure the rate of expansion of the universe. The expansion of the universe has profound implications for the shape of space. If the universe is expanding, then it must have originated from a much smaller, denser state. This idea forms the basis of the Big Bang theory, which describes the origin of the universe as a rapid expansion from a singularity. The light from distant galaxies has allowed us to trace the history of the universe from this initial moment, revealing its evolution from a hot, dense state to the vast, cold cosmos we observe today. But light, as we've seen, does not just reveal the past, it also provides clues about the future. One of the most surprising discoveries of the past few decades has been the realization that the expansion of the universe is accelerating. In the late 1990s, astronomers discovered that distant supernovae, which are exploding stars, were fainter than expected, indicating that they were farther away than they should have been if the universe's expansion was slowing down. This discovery led to the realization that something unknown, dubbed dark energy, is driving the accelerated expansion of the universe. Dark energy, like dark matter, is one of the greatest mysteries of modern cosmology. While dark matter is believed to make up the majority of the mass in the universe, dark energy is thought to account for most of the universe's energy, driving its expansion. The study of light and the way it interacts with dark energy is key to understanding the ultimate fate of the universe. Will the universe continue to expand forever, growing colder and emptier as stars burn out and galaxies drift apart? Or will the expansion slow, leading to a big crunch in which the universe contracts back into a singularity? The study of light, from the cosmic microwave background to distant supernova, has revealed much about the shape and future of the universe. Light, in all its forms, serves as our cosmic messenger, carrying information across vast distances and revealing the hidden structure of the cosmos. By studying how light bends, stretches, and shifts, we gain a deeper understanding of the fabric of space itself, the very geometry that underlies the universe. As we continue our exploration of the cosmos, light will remain our most powerful tool for uncovering the mysteries of space. Whether it's the bending of light around a black hole, the redshift of distant galaxies, or the faint echoes of the Big Bang, light holds the key to understanding the vast and complex universe in which we live. It is through the study of light that we continue to unravel the deep structure of space, moving ever closer to understanding the true nature of the cosmos. As our exploration of the universe deepens, we arrive at the profound realization that gravity, once thought to be a mysterious force acting at a distance, is in fact an intrinsic property of the very fabric of space and time. The idea that gravity is a force, as described by Newton, is replaced by an elegant and transformative understanding introduced by Albert Einstein. Gravity is geometry. The presence of mass and energy distorts the fabric of spacetime, and it is this curvature that governs the motion of objects in the universe. Einstein's theory of general relativity, formulated in 1915, revolutionized our understanding of gravity. In this theory, space and time are not separate, unchanging entities, but are part of a unified four-dimensional fabric called spacetime. Instead of treating gravity as an invisible force acting through space, Einstein proposed that massive objects, such as planets and stars, cause spacetime to curve around them. The more massive an object, the greater the curvature it creates in spacetime, and the stronger the gravitational pull it exerts on nearby objects. This concept fundamentally shifts the way we think about gravity. It is not a force pulling objects together, but a manifestation of the curvature of spacetime itself. To visualize this, imagine a heavy ball placed on a stretched-out rubber sheet. The ball causes the sheet to dip and curve around it. Now, if you place smaller objects on the sheet, they will roll toward the ball, not because the ball is pulling them, but because the surface of the sheet is curved in such a way that their paths are deflected toward it. Similarly, in the curved fabric of space-time, objects like planets and stars follow paths dictated by the curvature, and their motion appears as if they are being pulled by gravity. This simple analogy of a rubber sheet has limitations, of course, since it only represents 2 dimensions of spacetime. In reality, spacetime is 4-dimensional, 3 spatial dimensions and 1 temporal dimension. Nonetheless, the core idea remains. The presence of mass and energy curves spacetime, and this curvature is what we perceive as gravity. One of the most profound implications of this theory is the idea that light, like matter, is affected by the curvature of spacetime. In Einstein's framework, light doesn't travel in straight lines. Instead, its path bends when it passes near massive objects. This phenomenon, known as gravitational lensing, was first observed in 1919 when Arthur Eddington's team confirmed that light from distant stars bent as it passed near the Sun during a solar eclipse. This observation provided strong evidence for Einstein's theory and showed that gravity does not just affect matter, but also governs the path of light itself. General relativity also predicts the existence of black holes, regions of spacetime, where the curvature becomes so extreme that not even light can escape. These cosmic entities, with their event horizons and singularities, are the most extreme manifestations of spacetime curvature. The intense gravitational field near a black hole bends space and time in such a way that all paths, including that of light, lead toward the singularity at the center, beyond which nothing can escape. But it is not just black holes that demonstrate the power of spacetime curvature. Einstein's theory also predicted that the presence of mass and energy would cause the fabric of spacetime to warp in subtle ways, affecting the flow of time itself. This effect, known as time dilation, means that time passes more slowly near massive objects and faster in regions of lower gravity. This effect, though small on Earth, becomes more pronounced near massive stars or black holes. For example, the closer an object gets to a black hole, the more time slows down for it relative to an observer farther away. Time, in a sense, bends along with space, creating a deep connection between the two. One of the most striking predictions of general relativity is the concept of gravitational waves, ripples in spacetime caused by the acceleration of massive objects, such as merging black holes or neutron stars. These waves propagate outward from the source at the speed of light, stretching and compressing spacetime as they travel. For decades, gravitational waves remained purely theoretical until their detection in 2015 by the LIGO experiment. This groundbreaking discovery confirmed a key prediction of Einstein's theory and opened a new window for observing the universe. General relativity also provides the framework for understanding the large-scale structure of the cosmos. The universe itself, with its vast galaxies and clusters of galaxies, is not static, but expanding. The fabric of space-time stretches, and this expansion affects the motion of galaxies and the overall evolution of the universe. The expansion of the universe is a direct consequence of the geometry of spacetime and its interactions with matter and energy. The theory of general relativity is not just a scientific revolution, it is an elegant framework that reshapes our understanding of space, time, and the universe. It tells us that gravity is not a force acting at a distance, but a curvature in the fabric of spacetime caused by the presence of mass and energy. This insight has led to numerous breakthroughs in our understanding of the cosmos, from the behavior of black holes to the dynamics of the expanding universe. Yet, while general relativity has been incredibly successful in explaining a wide range of phenomena, it is not the final word on the nature of space and time. One of the great challenges of modern physics is to reconcile general relativity with quantum mechanics, the theory that describes the behavior of particles on the smallest scales. The two theories, though both immensely successful in their respective domains, are fundamentally incompatible. General relativity describes a smooth, continuous spacetime, while quantum mechanics operates on the assumption that space and time are discrete and probabilistic at the smallest scales. The search for a theory of quantum gravity, which would combine general relativity and quantum mechanics into a single unified framework, is one of the most pressing challenges in theoretical physics. Ideas such as string theory and loop quantum gravity are promising candidates for this elusive theory. But as of yet, a complete understanding of quantum gravity remains out of reach. Nevertheless, Einstein's theory of general relativity stands as one of the greatest achievements in the history of science. It has transformed our understanding of the universe, showing us that space and time are not immutable stages on which events unfold, but dynamic, flexible fabrics that can bend and stretch in response to the objects within them. The concept of gravity as geometry is a profound insight into the nature of reality, and it continues to guide our quest for understanding the cosmos at both the largest and smallest scales. As we continue our journey through the universe, we will see how the curvature of spacetime, as described by general relativity, has profound implications for everything from the behavior of light and the formation of galaxies to the fate of the universe itself. The elegant river of spacetime, flowing and bending around the massive objects within it, is the foundation upon which our understanding of the cosmos is built. As we delve deeper into the nature of space and its role in shaping the universe, we encounter a strange and subtle feature of the cosmos, the quantum vacuum. For all its apparent emptiness, this vacuum is anything but still. In fact, it is a seething, dynamic field filled with invisible activity and fluctuations, where particles pop in and out of existence, and where the very fabric of spacetime itself is subtly disturbed. The concept of the quantum vacuum arises from the theory of quantum mechanics, which governs the behavior of particles on the smallest scales. Quantum mechanics tells us that particles do not have precise, fixed positions and velocities. Instead, their properties are defined by probabilities. In this probabilistic world, the vacuum is not an empty void, as we might intuitively think, but rather a sea of fluctuating energy. These fluctuations are a direct consequence of the uncertainty principle, one of the foundational concepts of quantum mechanics. The uncertainty principle, formulated by Werner Heisenberg, states that we cannot simultaneously know both the position and the momentum of a particle with absolute precision. This uncertainty implies that even in a region of space that seems to be empty, there must be some underlying energy fluctuations. These fluctuations are not merely theoretical. They have real, measurable effects, and they play a crucial role in many physical phenomena. One of the most striking manifestations of the quantum vacuum is the Casimir effect, which occurs when two uncharged conducting plates are placed very close to each other in a vacuum. According to quantum theory, the vacuum is filled with virtual particles, pairs of particles, and antiparticles that briefly appear and annihilate each other. The presence of the plates alters the nature of these virtual particles near the plates, causing a measurable force that pushes the plates together. This force, though extremely small, is a direct result of the quantum vacuum's fluctuations and has been experimentally verified. The quantum vacuum is also thought to be responsible for another remarkable phenomenon, the creation of virtual particles. In a vacuum, pairs of virtual particles can spontaneously form and annihilate in a fraction of a second. These particles, though short-lived, are not just a theoretical curiosity. They play an important role in the behavior of matter and energy. For example, in the process of Hawking radiation, a pair of virtual particles can form near a black hole, with one particle falling into the black hole and the other escaping as real radiation. This process suggests that black holes can slowly lose mass over time, a discovery that has profound implications for our understanding of these enigmatic objects. Another intriguing consequence of the quantum vacuum is its role in the phenomenon of vacuum energy. This is the energy that arises from the fluctuations of the quantum vacuum itself, and it has a significant impact on the universe's large-scale behavior. In the 1990s, astronomers discovered that the expansion of the universe is accelerating, a discovery that led to the introduction of the concept of dark energy, a mysterious force thought to be responsible for the accelerated expansion. Some theories suggest that dark energy is a manifestation of vacuum energy, a result of the quantum vacuum's fluctuations. If this is true, it means that the vacuum of space is not just empty. It is filled with an energy that has the power to shape the very evolution of the universe. These ideas challenge our classical understanding of the vacuum as a simple emptiness, a space devoid of matter and energy. Instead, the quantum vacuum reveals that even the most seemingly empty regions of space are filled with potential that can have real, physical consequences. The quantum vacuum is a dynamic, active environment, full of energy, particles, and forces that shape the universe in ways we are only beginning to understand. One of the most profound insights of quantum field theory is that the vacuum is not a passive backdrop against which the events of the universe unfold. Instead, it is an active participant in the creation and destruction of particles, and it is the stage on which the entire quantum world plays out. In this view, the universe itself is not simply made of matter and energy, but also of the quantum fluctuations that permeate all space. These fluctuations give rise to the fundamental particles that make up the matter around us and drive the interactions between them. This understanding of the vacuum as a seething, dynamic field challenges our intuitive notions of space as empty. And still, the quantum vacuum, with its virtual particles and fluctuating energy, is a far cry from the classical notion of emptiness. It is not a nothingness, but a rich, complex environment filled with possibilities. And its activity has profound implications for everything from the formation of stars to the evolution of the universe itself. The quantum vacuum also raises important questions about the nature of time and space. If the vacuum is filled with fluctuating energy, how does this energy interact with the fabric of spacetime itself? In general relativity, we learn that the presence of mass and energy curves spacetime. But does the quantum vacuum contribute to this curvature? Some theories, such as quantum gravity, suggest that the fluctuations of the quantum vacuum might influence the structure of spacetime at the smallest scales, leading to a deeper understanding of the very fabric of the universe. As we continue to explore the mysteries of the quantum vacuum, we find that it holds the keys to understanding some of the most fundamental questions about the universe. What is the true nature of space and time? How does the quantum world connect with the fabric of spacetime described by general relativity? And what role does the quantum vacuum play in the creation and evolution of the universe? These questions remain at the forefront of modern physics, and the answers we seek may reveal an entirely new understanding of the cosmos. In the next stages of our exploration, we will continue to grapple with these mysteries, seeking a unified framework that can describe both the microscopic world of quantum mechanics and the macroscopic world of general relativity. The quiet activity of the quantum vacuum, though elusive, provides the foundation for the universe's most fundamental processes, and it is through the study of this unseen world that we hope to unlock the deepest secrets of reality. As we explore the nature of space, the universe, and the very fabric of reality, we encounter one of the most intriguing concepts in modern physics and mathematics, topology. While we've already seen how topology helps us understand the shape and curvature of space, it also allows us to delve deeper into the hidden properties of the universe. Properties that are not immediately apparent but are fundamental to its structure. One of the most profound aspects of topology is its focus on invariance features of a space that remain unchanged even when that space is stretched, bent, or deformed. A key concept in topology is the idea of a hole in space. In Euclidean geometry, we tend to think of space as an empty expanse, but topology reveals that space can have more subtle features, like holes that are preserved no matter how much space is distorted. These topological holes can take many forms: a simple hole in a donut, a more complex hole in a torus, or even higher dimensional holes in more abstract spaces. What makes these holes so interesting is that they are topological invariants. No matter how much the space is stretched or deformed, the number and type of holes remain the same. This invariance provides a powerful tool for understanding the deep structure of the universe. One of the most fascinating examples of topological holes in the universe is the concept of a wormhole. A wormhole, in theoretical physics, is a passage through spacetime that connects to distant points in the universe. It can be visualized as a tunnel with two ends at separate points in spacetime, and its structure is often likened to a hole in the fabric of the universe. The idea of a wormhole arises from Einstein's theory of general relativity, and while no wormholes have been observed, they remain a popular subject in both theoretical physics and science fiction. Wormholes are not the only places where topological holes appear in our understanding of the universe. The study of black holes, those enigmatic regions where gravity is so intense that not even light can escape, also reveals deep topological features. A black hole's event horizon, its boundary, beyond which nothing can escape, is itself a feature. The study of black holes and their singularities, the points at which the curvature of spacetime becomes infinite, has provided insights into the very nature of space and time. These singularities represent holes in the fabric of spacetime, and understanding their topology is key to unlocking the mysteries of black hole formation and behavior. In fact, some physicists have proposed that the very structure of spacetime might be filled with a network of holes and defects akin to a topological lattice. These hypothetical structures, which could be made up of quantum foam, might provide a bridge between the quantum and classical worlds, offering a way to describe both the small-scale behavior of particles and the large-scale behavior of spacetime itself. This vision of spacetime as a topological structure is still in its infancy, but it represents an exciting frontier in theoretical physics, one that could lead to a deeper understanding of the nature of reality itself. In addition to understanding the structure of the universe at large scales, topology also plays a crucial role in the study of condensed matter physics, particularly in the study of materials with unusual and exotic properties. For example, materials known as topological insulators have been found to have unique electronic properties, where the surface of the material behaves in a way that is completely different from its interior. These materials are a direct consequence of topological effects, and they have important implications for future technologies, such as quantum computing. The study of topological phases of matter is a rapidly growing field, with new discoveries being made all the time. Topology also provides a powerful framework for understanding the behavior of systems that exhibit symmetry, a property of space that underlies many of the laws of physics. Symmetry is crucial in physics because it allows us to make predictions about how objects behave in different environments. For example, the symmetry of a circle, where every point is equidistant from the center, is fundamental to understanding the orbits of planets and the motion of objects in space. In quantum mechanics, symmetry also plays a central role in determining the behavior of particles and their interactions. The study of topological invariants can provide insight into how symmetry operates in physical systems, revealing deep connections between the abstract world of mathematics and the physical world. Topological wholes and invariants also help us understand the large-scale structure of the universe. In cosmology, the study of the topology of the universe provides clues about its shape and how it evolved. Some theories suggest that the universe may have a non-trivial topology, meaning it is not simply a three-dimensional space, but one that could be folded or curved in such a way that it connects back on itself. This idea, known as closed universe topology, suggests that if you travel far enough in one direction, you could eventually return to your starting point. Much like traveling around the surface of the Earth, the study of the universe's topology could provide answers to some of the most profound questions in cosmology, such as whether the universe is infinite or finite, and whether it has a boundary or is unbounded. The role of topology in understanding the universe is still being explored. But it is clear that topological concepts like wholes, invariants, and connectivity are fundamental to our understanding of space and reality. Whether we are studying the large-scale structure of the cosmos, the behavior of light near black holes, or the quantum properties of materials, topology offers a powerful tool for revealing the hidden connections that shape the universe. Through the study of topological features, we can gain deeper insights into the nature of spacetime, the behavior of matter and energy, and the fundamental laws that govern the cosmos. As we move forward in our exploration of the universe's deep structure, the role of topology will only become more pronounced. Whether it is in the study of black holes, the topology of the universe itself, or the exotic properties of quantum materials, topology provides a framework that allows us to think about space in new and exciting ways. By understanding the wholes and invariants that underpin the universe, we can gain a clearer picture of the true nature of reality itself. As we come to the final chapter in our exploration of space, geometry, and the vast, intricate fabric of the universe, we find ourselves faced with a profound realization. Nothingness, once thought of as the absence of all things, is far more complex and meaningful than we could have ever imagined. Our journey has taken us from the ancient debates about the nature of the void to the modern understanding of the quantum vacuum, from the flat world of Euclidean geometry to the curved and dynamic landscape of general relativity and cosmology. And along the way, we have learned that the nothing we once took for granted is actually a rich, active environment, one that influences everything from the behavior of light to the evolution of the cosmos itself. The study of space has revealed that what we call nothing is, in fact, a dynamic, living presence full of fluctuations, energy, and potential. Whether we're looking at the mysterious quantum vacuum, where particles flicker in and out of existence, or the curvature of spacetime, where gravity shapes the motion of galaxies, we see that nothingness is never truly empty. It is, instead, full of hidden activity, shaping the universe in ways we are only beginning to understand. One of the most profound insights we've gained on this journey is the realization that space is not a passive, unchanging backdrop against which events unfold. Rather, it is an active participant in the drama of existence. From the curvature of spacetime in general relativity to the quantum fluctuations of the vacuum, space itself is a malleable, responsive entity, an entity that bends, stretches, and transforms in response to the energy and mass within it. The mathematics of geometry and topology have allowed us to understand how space can be curved, how it can have holes, and how it can behave in ways that defy our everyday intuitions. But these abstract concepts are not just mathematical curiosities. They are the very foundation of the universe. Whether it's the bending of light around black holes, or the expansion of the universe itself, the geometry of space shapes everything. We observe, space is not just a container for objects. It is a dynamic, evolving entity that influences how objects move, interact, and change over time. In the world of quantum mechanics, we find that the quantum vacuum, with its infinite fluctuations, plays a central role in the creation of particles and forces. These fluctuations are not random noise. They are the fundamental building blocks of reality, shaping everything from the behavior of elementary particles to the large-scale structure of the universe. The vacuum, once thought of as mere emptiness, is revealed to be a profound source of energy and activity, an invisible field that gives rise to the very particles and forces that make up our universe at the same time. We have come to understand that the universe itself may be far more complex than we ever imagined. The idea of a finite, curved universe, or a universe with a non-trivial topology, challenges our assumptions about space, time, and the very nature of existence. Whether we are considering the large-scale curvature of the cosmos or the microscopic behavior of particles, we see that space is not fixed but dynamic, constantly evolving, stretching, and reshaping itself in response to the mass and energy it contains. In the end, the study of nothingness of the void, the vacuum, and the deep structure of space has revealed that nothing is not a concept of absence, but of potential. The universe is not empty. It is full of possibilities. Whether it's the fluctuations of the quantum vacuum, the bending of space-time by massive objects, or the topological features of the universe, we see that nothingness is a fertile ground for the emergence of structure, matter, and energy. The universe, it turns out, is much more than the sum of its parts. It is a living, breathing entity, shaped by the invisible forces of geometry, topology, and quantum mechanics. As we conclude this journey, we are left with a deep sense of awe and wonder. The universe is far more complex, interconnected, and dynamic than we ever imagined. The shape of nothingness is not empty or insignificant. It is the foundation of everything we see, from the smallest particles to the largest galaxies. The more we learn about the geometry and structure of space, the more we realize that the universe is not a cold, indifferent void, but a vast, living network of interconnected forces and energies, a network that gives rise to the very fabric of reality itself. The journey of discovery is far from over. As we continue to explore the mysteries of the cosmos, we will uncover more about the shape of space, the nature of time, and the hidden structure of the universe. But for now, we can pause and reflect on what we've learned, that nothingness, in all its complexity and wonder, is not an absence, but a presence that shapes the universe in ways we are only beginning to understand in this quiet, expansive space where the boundaries of knowledge and imagination meet. We find that the universe is not a static, predictable entity, but a living, breathing system of relationships and forces. The shape of nothing is, in the end, the shape of everything, a shape that is constantly changing, constantly evolving, and constantly revealing new secrets about the universe and our place within it. As we look up at the stars, we can feel the weight of the void beneath our feet, a void that is full of life, full of energy, and full of the potential to shape the future of the universe itself.